Welcome to the another class of design of RCC structure. In this class, the topic is design of doubly reinforced beam. In previous lecture, you have learned about doubly reinforced beam, the analysis of doubly reinforced beam, the basic concept of doubly reinforced beam. In this class, we are going to design a doubly reinforced beam with the help of limit state method. So let's check out the problem given. Design a rectangular beam 230 mm by 600 mm over an effective span of 5 meter. The superimposed load on the beam is 50 kN per meter. Effective cover to the reinforcement is taken 50 mm. Use M20 grade of concrete and Fe 415 steel. So in this question, the cross section is given, that means the depth is restricted. Now let's check how to design it. If the moment comes as per the question and as per the assumption what we will going to take, if moment comes is greater than the limiting moment, in that case you will definitely have to go for doubly reinforced beam. So let's start the solution. First, write down the given data. B, that means width is 230 mm. Capital D, that means overall depth is 600 mm. C, EFF, that means effective cover is 50 mm. That means effective depth small d is 600 minus 50, that is equals to 550 mm. The length, effective length is 5 meter. FCK is 20 Newton per millimeter square as grade of concrete is M20. Fy is 415 Newton per millimeter square as grade of steel is Fe 415, and imposed load given is 50 kN per meter. So first step is to find out the design load or factor load. The design load, to find out design load, first of all we have to find out the self weight. We know that self weight is, to find out self weight we have to multiply the cross sectional area of the beam with unit weight of RCC. So cross sectional area is 0.23 meter into 0.6 meter into the unit weight of RCC is 25 kN per cubic meter, that is equals to 3.45 kN per meter. Imposed load is given, that is 50 kN per meter. That means the total load is 53.45 kN per meter. Now we have to find out the design load. For that we have to apply the load factor, the partial safety factor from table 18 of IS 456 2000, that is 1.5 per dead load and live load combination. So now multiply the total load, that is 53.45 into 1.5, that is equals to 80.175 kN per meter. Next step is to find out design moment, that is mu, and design shear, that is Vu. So mu is equals to WUL square by 8, that is equals to 80.175 into 5 square by 8, that is equals to 250.55 kN meter. That means mu is equals to, in this case, 250.55 kN meter, and the design shear Vu is WUL by 2, that is equals to 80.175 into 5 by 2, that is equals to 200.4 kN. So design shear Vu is 200.4 kN for this case. Next step is to find out limiting moment of resistance. So limiting moment of resistance mu lim is equals to 0.36 FCK into B into XU max within bracket D minus 0.42 XU max. We know that formula because we have already solved with this formula in case of single reinforced beam also, and this formula is given in Annex G of IS 456 2000. Now we have to put all the values in formula to find out the value of mu limit, right? We have already all values except XU max. For Fe 415 grade of steel, XU max is equals to 0.48 D. We know that it is also written in clause number 38.1 in IS 456 2000. So 0.48 into d small d is 550, that is equals to 246 mm. So value of XU max is 246 mm. So put the all values in this formula. So mu limit is equals to 0.36 into 20, that is FCK, into 230, that is B width, into 246, that is XU max, within bracket 550, that is effective date, minus 0.42 into 246, that is equals to 181966711.7 Newton mm. You may convert into kilonewton meter also. After getting this value, it is clear that mu is greater than mu limit. How? Let's check again. Look, the value of mu is 250.55 kilonewton meter and value of mu lim is smaller than that. So mu is greater than mu limit. Actually, the value which we have got for mu limit, it is in Newton mm. You may write this like 181.96 into 10 to the power 6 kilonewton meter. So this is how you can understand easily that the value of mu limit is less than mu. So the section is designed as doubly reinforced beam, right? So now we have to find out the value of mu2, the additional moment. Now the mu2 is equals to mu minus mu limit, right? So mu is 250.55 into 10 to the power 6 Newton mm minus the value which we have got for mu limit. So that is equals to 68583.288.3 Newton mm. You may also write in kilonewton per meter like 68.58 kilonewton meter. So now we have to find out the ratio, that is d dashed by d. So d dashed here is 50 and d is 550. So 50 by 550, that is equals to 0.09. Now we have to find out the value of Fs, right? So value of Fs, the stress in compression steel, we have to find out this from SP6 table F, but 0.09 is not given in the table, as you see earlier also. So let's check again. So look at table F of SP16, the value for 0.09 is not given, but value for 0.05 and value for 0.1 is given. As I told earlier in previous video, the link of that video you will got from description link. I have told there already that if we get any intermediate values, we have to take the upper value, okay, the greater value. So in this case we will definitely take the value of 0.1, and our grade of steel is 415, Fe 415. So value of Fs will be definitely 353. So as you see in table F of SP16, Fs is 353 Newton per millimeter square. So next step is area of compression steel. So in this step we will find out the area of compression steel and the number of compression bar required for this section, for this design. So formula is ASC is equals to mu2 by FSC into d minus d dashed. So to find out the area of compression steel, the formulas are already given, we have seen earlier. So mu2, we have to put the value of mu2, that is 68583.288.3 by FSC is 353 multiplied by within bracket d, that is 550 minus d dash, that is 50. So the value of ASC the area of compression steel is 388.6 millimeter square. Now using 16 diameter bar, we have to find out the number of bars which we have to provide. So area of one bar is pi by 4 into 16 square, that is 201 mm square. Now number of bars required is total area of compression steel by area of one bar, that is equals to 1.93. So you know that we can't provide 1.93 numbers of bar, so we have to definitely provide a little larger value. We have to provide here, we will provide two numbers of 16 mm diameter as compression steel. So that's why ASC provided is definitely will be increased. So for two numbers of bar, area of steel in compression provided, ASC provided, will be 402 mm square. Now the next step is area of tension steel, AST. In this case also we will definitely find out the area of tensile steel and the number of bars which we have to provide for this case. So AST1 is equals to mu lim by 0.87 Fy within bracket D minus 0.42 XU max. That is equals to, now put the value of mu lim, that is 181966711.7 by 0.87 into 415 within bracket 550 minus 0.42 into 246 bracket close. So from this we will get the value of AST1, that is equals to 1128.3 mm square. Now AST2, the additional reinforcement, so that is equals to mu2 by 0.87 Fy into t minus d dash, that is equals to, the value of mu2 is 685832288.3 by 0.87 into 415 into within bracket 550 minus 50. So the value of AST will be 380 mm square. So these two formulas are already given in Annex G of IS 456-2000. So in previous lecture I have already shown the formula where the formula is in Annex G, and I have already write there in detail the formula. So for this you have to go my previous video of design of doubly reinforced beam. Okay, so we have get in the AST1 for limiting moment, and for additional moment AST2. So total AST is equals to definitely AST1 and AST2. So 1128.3 plus 380, that is equals to 1508.3 mm square. This is the area of tension steel required. Okay. Now we use 20 mm dia bars. So number of bars required, definitely AST by the cross sectional area of one bar. So 1508.3 by pi by 4 into 20 square, that is equals to 4.8. So definitely we can't provide again 4.8 number of bars, so we have to provide 5 number of bars. To provide 5 numbers of 20 mm diameter bars, and so definitely area of steel in tension will be increased for that. So AST provided is 1570 mm square. Now we may curtail 50% of bar at support. So there is 5 numbers of bars in tension zone. We may curtail 2 numbers of bar in length only. So how much length we may cut? That is, out of them 2 bars are curtailed at a distance of 0.08 L, that is equals to 0.08 into 5 meter, that means 5000 mm, that is equals to 400 mm from the supports. So from the both support we may curtail 2 numbers of bars in length of 400 mm. So design almost done, and the next step is check for deflection. We have to check now. So check for deflection, first of all we have to find out the percentage of steel. In this case, in case of doubly reinforced beam, there we have to find out two types of percentage of steel in case of tension reinforcement and in case of compression reinforcement. So for tension reinforcement, percentage of steel P suffix T is equals to 100 AST by BD. So that is equals to 100 into 1570 by 230 into 550, that is equals to 1.25%. And percentage of steel in compression, that is equals to P suffix C, that is percentage of steel in compression, that is equals to 100 into ASC by BD. So you know ASC is area of compression reinforcement, as AST is area of tension reinforcement. So 100 into ASC in that is 402 by B is 230 into D is 550, that is equals to 0.31%. So now we have to find out Fs, because we have to find out the value of modification factor from figure number 4 and figure number 5 of IS 456 2000. So Fs is 0.58 into Fy by AST squared by AST provided, that is equals to 0.58 into 415 into 1508 by 1570, that is equals to 231 Newton per millimeter square. So Fs is 231 Newton per millimeter square. Okay. So now from figure 4 we have to find out modification factor for tension reinforcement, and from figure 5 we have to find out modification factor for compression reinforcement of IS 456 2000. So this is the calculation, but before that let's check out figure 4 and figure 5 how the values comes. So let's check figure 4 in your screen. So for percentage of steel 1.25 and Fs 231. So Fs 231 is not given in this graph, in this chart. So but Fs 190 is given, Fs 240 is given. So definitely Fs 231 is lies between Fs 190 and Fs 240. And for 1.25 you may look you can look here in it is definitely greater than 1.2 in x-axis. So it is approx for 190 the modification factor is 1.12, and for Fs equals 240 for this modification factor is approx 0.95. So from this we have to calculate the modification factor. So let's go to the note. Look, modification factor in for tension reinforcement, that is equals to 1.12 minus 1.12 minus 0.95 by 240 minus 190 multiplied by 231 minus 190, that is equals to 0.98. So these values we get from figure 4 as you see. So this modification factor we have already find out. Now we have to find out modification factor for compression reinforcement from figure 5 of IS 456 2000. You can see figure 5 of IS 456 2000 in your screen. So for percentage 0.31, which we already found out. For 0.31 we have to find out this, but in graph this is written for 0.5, that means the middle portion is 0.25, and the exact value of 0.25 we can get from this graph. 0.31 is definitely lies between this 0.25 and 0.5. So we can assume that value from here. So from these values we can check that. So one benchmark is our 0.25 and another benchmark is 0.5, because this is given in our chart in a figure 5, right? So for 0.5 percentage of steel, it is approximate modification factor is 1.14, and for 0.25 it is approx 1.08, right? So let's go to the notes and check it out. So in notes you can see So 1.08 plus 1.14 minus 1.08 by 0.5 minus 0.25 multiplied by 0.31 minus 0.25, that is equals to 1.09. So these values we have checked from figure 5, right? So now L by G max, length to depth ratio maximum, is equals to 20. This value 20 is we get from simply supported beam, and the closed number is 23.2.1 of IS 456 2000. So 20 into modification factor in tension reinforcement and modification factor for compression reinforcement. So 20 into 0.98 into 1.09, that is equals to 1.36. So this is length to depth ratio maximum, L by G max, and L by G provided our actual length by actual effective depth, that is 5000 by 550, that is equals to 9.09. So L by G max is greater than L by G provided, hence okay, and it is safe for deflection, right? So, next step is design of shear. So design shear value already we have get VU is 200.4 kilonewton. So tau V is equals to VU by BD, that is equals to 200.4 into 10 cube by 230 into 550, that is equals to 1.58 Newton per millimeter square. That means the value of tau V is 1.58 Newton per millimeter square. Now AST at support, as we know, two bars are curtailed at support. So area of steel is support is for 3 bars, 3 number of bars. So 3 into pi by 4 into 20 square, that is equals to 942 mm square, and the percentage of steel is 100 into AST by BD. So 100 into 942 by 230 into 550, that is equals to 0.75. So for M20 concrete and percentage of steel 0.5, from table 19 of IS 456 2000, the tau C will be 0.56 Newton per millimeter square. So, and from table 20, tau C max is equals to 2.8 Newton per millimeter square, which is greater than tau C, hence okay. Okay, so let's check once table number 19 and table number 20 of IS 456 2000. So look at table 19 of IS 456 2000. So tau C is for 0.75 percentage of steel, and M20 grade concrete is 0.56, which we have write already in our notes. So this is the value of tau C, and value of tau C max from table number 20 for M20 concrete, that is 2.8. So tau C max is greater than tau C, hence okay. Let's go to notes. Now look, tau V is greater than tau C, right? So hence shear reinforcement is to be provided definitely. So for shear reinforcement, VUS is equals to VU minus tau CVD. VUS is 200.4 into 10 cube minus tau CVD is 0.56. That is also we get from IS 456 into 230 into 550. That is equals to 129560 Newton. So the value of tau CVD where we get from IS 456 2000, that is given in the problem of single reinforced beam. You may go there for detailed description, already given there. Okay. Now using two-legged 8 mm diameter vertical stirrups. Okay, so ASV, that means area, 2 into pi by 4 into 8 square, that is equals to 100.5 mm square. Now spacing of stirrups, that is SB is equals to 0.87 Fy ASB into D by VUS, that is equals to 0.87 into 415 into ASB is 100.5 into D is 550 by VUS is 129560, that is equals to 154 mm, say 150 mm. okay, we may decrease the value of spacing. And spacing as per normal reinforcement from same formula, SB is equals to 0.87 Fy ASB by 0.4 B. You have seen this formula in previous videos. So that is equals to 0.87 multiplied by 450 multiplied by 100.5 by 0.4 into 230. That is equals to 394 mm. So the maximum spacing definitely should be less of these all, and 0.75 D equals to 0.5 into 550, that is equals to 412.5 mm, 300 mm, and from previous to the minimum value then is 150 mm. So we have to provide 2-legged 8 mm dia stirrup at the rate 150 mm center to center. So design is complete, and as per design data, this is the drawing. You have to drawing after every design completion. Okay, so in various colors, everything is shown here. You can find out everything, like in longitudinal section at left figure, the center distance, span distance is 5 meter. If it span is 5 meter, curtailment is shown 400 mm in both sides. At support, 3 numbers of 20 mm dia bars is written. At mid span, 5 numbers of 20 mm dia bars. Stirrups are 2-legged 8 mm dia at the rate of center to center. In compression zone, 2 numbers of 16 mm diameter bar is given. Now on this right picture for cross sections, there are 2 pictures of cross section. Okay, one for cross section at mid span and one for cross section at support. So 2-legged 8 mm dia stirrup at the top center to center. You can also see here there are 2 numbers of bar at top at compression zone and 5 numbers of 20 mm dia bar at bottom portion. So you have to draw this also. Okay, so that's all for this class and for doubly reinforced beam design. Thank you.